Welcome back. Today, I'll describe coordinate frames for space navigation and simulation calculations. There are two reference frames, or coordinate systems, that are especially important for space flight. One is Earth-centered and called the Geocentric Equatorial Coordinate System, or Earth-Centered Inertial, ECI, reference frame. The origin of this coordinate system is the center of Earth, and its z-axis points toward the North Pole. The xy-axis plane is Earth's equatorial plane, and the x-axis points toward vernal equinox. I show this in the image on my right. This reference frame does not rotate with Earth, and it is normally used for near-Earth space operations. It is not a true inertial reference frame because Earth is moving slowly around the Sun. However, its orientation is fixed relative to the stars. This is a right-hand coordinate system defined as follows. If you point the fingers of your right hand in the x-axis direction and then curl another finger into the direction of the y-axis, your thumb will be pointing in the direction of the z-axis. I show this in the image that you now see. Another reference frame is the heliocentric ecliptic coordinate system. The origin of this coordinate system is the center of the Sun. Its xy-axis plane is the Earth's orbital, or ecliptic, plane around the Sun, and, like the ECI frame, the x-axis points toward the vernal equinox. This coordinate system can be used for space operations in our solar system, such as missions to Mars. This coordinate frame is also not a true inertial reference frame because even the Sun travels through space relative to the stars. A true inertial reference frame is one that's referenced to the stars and has a center that doesn't move relative to the stars. Why do we need to get as close to an inertial reference frame as possible? Because the spacecraft navigation computer finds velocity and position by integrating measured accelerations in all three axes, and acceleration is always measured relative to the fixed inertial reference frame. For short missions, use of the Earth-centered reference frame will produce errors, but will be good enough for short missions. For longer duration flights in our solar system, we need more accuracy, so we must use a reference frame that's closer to the true inertial frame, a sun-centered frame. You can use coordinate transformations to convert from one coordinate system to another. To do this, you must know how the two reference frames move relative to each other and their relative orientations. We hope you found this video useful. It's important because in the next video, we'll use this ECI frame to solve the spacecraft's equation of motion. And that equation allows us to calculate spacecraft flight for any orbit or trajectory. We plan to produce more videos in the future, so subscribe to this channel if you want to see more videos describing space flight and orbital mechanics. We also need your feedback, so please leave comments. Goodbye.